Hello everyone. So we are going to solve question number 2 from paper 2 Feb March 2022 series. Let's start by reading the question. Water leaves the end of a hose pipe at point P with a horizontal velocity of 6.6 meter per second as shown in figure. So this is a hose pipe and water leaves it at a horizontal velocity of 6.6 meter per second. So I will just label it as Vx since it's the horizontal velocity. But one important thing to note here is that this is the entire velocity which water has at this point. So the only component this water has is its horizontal component. So at this point, this is the entire resultant velocity. It has 6.6 meter per second in the horizontal direction. And you can see clearly from the figure that as the water falls down, as it comes out of the hose pipe, it takes a trajectory, a projectile path, and goes all the way from point P to point Q, which is on the ground, which is how you would expect water to fall down. Point P is at a height h above the ground, so h is the vertical displacement of water here. So I will just label it as Sy, displacement along the y direction. The water hits the ground at point Q. The horizontal distance from P to Q is 3.5 meter, which is labeled over here. So this becomes the displacement of water along the x direction. So we have got the displacement along the x direction, we have got the velocity along the x direction. Now let's move ahead. Air resistance is negligible. Now, air resistance is negligible. Whenever we read this, it should immediately come to our mind how does it translate into in terms of velocities in our question. Since we can clearly see this is a situation of motion in two dimension because water is traveling both along the x and the y directions. So in motion, in cases of motion in two dimension, having a negligible air resistance means that the horizontal component of the motion will be uniform motion, which means that Vx will remain constant throughout the situation, whereas vertical motion will be uniformly accelerated motion with an acceleration equal to g. Let's move ahead. Assume that the water between P and Q consists of non-interacting droplets of water. Non-interacting droplets of water means that the droplets of water do not apply any force on each other and that the only force acting on each droplet is its weight. So as water falls down, there is only one force acting on water, which is its weight, which is a force we all know x vertically downward. So that is the only unbalanced force acting on water at the moment. There is no horizontal force, there is no other vertical force as well. Explain briefly why the horizontal component of velocity of a droplet of water remains constant as it moves from P to Q. Just a while back, we spoke about having negligible air resistance, and we said that negligible air resistance would mean that the horizontal component of velocity remains constant. Now, here we have to explain why is that so. So, for that, we will quickly look at why or how would velocity even change. We know from the definition of acceleration that a change in velocity per unit time is known as acceleration. So whenever there is a change in velocity, there has to be some acceleration. And acceleration by definition only occurs whenever there is an unbalanced force acting on a mass. So if there is an unbalanced force, that would produce an acceleration. And when there is an acceleration, there would be a change in velocity. Now, if you look at the situation of these droplets of water, as they travel from point P to Q, they have only one force acting on them, which is a vertical force. There is no horizontal force acting on these droplets, which means there will be no horizontal force, which means there will be no horizontal acceleration. As a result, the change in horizontal velocity will also be zero, which means the horizontal velocity will also remain constant. So now let's put it into words. Since there is no resultant or unbalanced force along the horizontal direction. Therefore, there is no acceleration in this direction. Hence, the velocity remains constant. Okay, moving ahead. Next part. Show that the time taken for the drop for a droplet to move from P to Q is 0.53 seconds, which means the time it takes for reaching from P to Q. Now, we all know in projectile motion we have to consider the vertical and the horizontal components separately. So here we can take any of the two components for which we know the variables. Let's talk about the horizontal component first. We already know the horizontal velocity, Vx, which remains constant throughout the motion. We know already the horizontal displacement, and now we need to find out the time for the entire motion. We can simply use the basic definition of velocity, which is rate of change of displacement. And since I'm writing it all for horizontal component, I'm using the subscript x with the velocity and the displacement. I can rearrange the equation making t my subject, and I end up getting sx over vx. As a result, I will get 3.5 divided by 6.6, and the calculations will give me 0.53 seconds, which is exactly what we had to prove. 0.53 seconds. So this is my answer. Calculate height h. That is the next part. Now, if you remember from the diagram, height h is nothing but the vertical displacement of the droplets. Now, for vertical motion, what are the variables that we know about? Let's have a look at the diagram. Initially, we have already been told that droplets have only a horizontal velocity, which means the initial vertical velocity is actually a zero. Vertical motion is uniformly accelerated motion, which means the acceleration is equal to the acceleration due to free fall, which is 9.81 meter per second square. So I will just write down these variables over here. I know the initial vertical velocity, I know the acceleration, and I also know the total time of motion, which I calculated previously, and I'm interested in finding out the vertical displacement. So we have to think of an equation which contains all of these variables, out of which s is the only unknown. So we can use this equation over here, s equals ut plus half at square. U in our situation is 0. So I will just write it with in terms of the variables used in the question. In place of s, I wrote h, which is the height. Ut becomes 0 multiplied by t plus half at square. Half a is equals to 9.81 meter per second square. And here we're not taking 9.8 to be a negative value because I'm sorry, it is half at square. So we are not taking a as a negative value because the motion is in the direction of gravity. So the speed or the velocity will increase with time. And the time we already calculated as 0.53. And on simplification, we will end up getting a value of 1.4 meters. Part D. For the movement of a droplet of water from P to Q, state and explain. State means we have to give a one line answer. Explanation means we have to explain it using some logic and reasoning, some equation maybe. State and explain whether the displacement of the droplet is less than, more than, or same as the distance along its path. So basically, we just have to differentiate between the distance and displacement in this particular situation. Let's have a look at the diagram. The distance traveled by the droplet is the entire distance traveled along this curved path, which we can see clearly in the diagram. Whereas the displacement, by definition of displacement, will be just a straight line path between P and Q, which clearly is a lesser amount, is lesser in magnitude than the total distance. So that the displacement between P and Q will be lesser then the total distance traveled by the droplets. Now, this is the statement, and the explanation part will give a reason. The reason comes here as the displacement is always the shortest path between the 2 points or a straight line path, whereas the total distance traveled is along a curve, which will obviously be a bigger value. Okay, moving on to the next part. Calculate the magnitude of displacement of a droplet of water that moves from P to Q. Diagram. Displacement between P to Q is the straight line drawn between P to Q. Now here the question nowhere mentions that the displacement has to be along the x direction or the y direction, which means we are not talking about the individual components of displacement. We have to calculate the total displacement from P to Q. For ease of understanding, I'll just draw this situation over here. If this is point P, displacement from P to Q is this diagonal line going all the way from P to Q. If I try to understand it in terms of components, this is how its components will actually look like. If this is point Q, so this is the displacement along the y direction, this is the displacement along the x direction, which by the way we know, we have calculated both of these previously. Sx, the displacement along the horizontal direction, was actually given in the question, and Sy we had calculated. So the total displacement is actually the resultant displacement, and since this becomes a right angle triangle, we can easily use Pythagoras theorem and write down an equation for the total displacement in this situation, which will be equal to the sum of the squares of the horizontal and the vertical displacements, or I will just root both sides. So substituting the values, I will end up getting an equation. I will just see the values from here, 3.5 and 1.4. So 3.5 is square plus 1.4 is square under root, and on simplification I end up getting an answer equal to 3.8 meters, which will be the total resultant displacement of the water droplets from P to Q. And that is the end of the question.